Okay, Common Core Algebra 2. So our next section in Chapter 3 is about multiplying matrices, and this is going to help us when we solve a system of equations with a matrix if we don't have our calculator for whatever reason. So I'm going to teach you how to actually do it longhand multiplying matrices, and then when we're in class we're going to talk about how to use some of the technology. So we can definitely do it with our TA83s and 84s or the Aspires if you have any of those calculators, and we'll do an Excel project too where we multiply matrices and we solve some systems of equations using matrices as well. So first thing, if we're going to multiply two matrices, so let's just say we're going to call them A and B, their product is going to be dependent on the dimensions of A and B. And in fact, sometimes you can't actually multiply two matrices if they don't have the right kind of relationship that we're going to talk about in a minute. Another big thing is like if we talk about in normal multiplication of just two numbers, you know, A times B is the same thing as B times A. So like 2 times 3 is the same thing as 3 times 2. But when we multiply matrices, it is not always necessarily the same. A times B is usually almost always different than B times A, and sometimes you can do A times B, but it doesn't necessarily mean that you can do B times A. The reason for that is that we can only do A times B if the columns of A, so the columns of A have to actually equal the rows of B, and that's going to give us a very specific set of dimensions. So what that could mean is like if we have A, let's say it has M rows and N columns, B then in order to multiply them has to have N rows and P columns. So these two numbers right here have to be equal, and that's going to give us our dimensions of the result are M and P. So let's say we had, let's make up some actual numbers here. A could be a 3 times 4, and if B was a 4 by 2, then since these two numbers are equal, the product of AB would be a 3 by 2. So I got that from those two numbers. But if I switch that, if I wanted to do a B times A product, I'd now have a 4 by 2 and a 3 by 4. But you see, these two are not equal, so there is no product possible here. Okay, so the big thing is that these two numbers have to be equal in order to have a product. So the rows of, or I'm sorry, the columns of A have to equal the rows of B. And if they're not equal, then we can't actually do the product. Okay, so what that would look like now if we actually do take the product. So we have a 2 by 2 times a 2 by 2. So these two are equal, which means our resulting matrix is going to be a 2 by 2, which I got from these two numbers. Okay, and to do that, to get that first position up here, so we're going to have some matrix, we're going to take our row 1 times our column 1. So we're going to multiply A times E plus B times G. And we'll do that for each one. So the first position is row 1, column 1. We take row 1 times column 1. To get that second position, we did A times F plus B times H. A times F plus B times H. And so on and so on. C times E plus D times G. C times F plus D times F. Now, this looks really complicated, and it is very easy to make a mistake in this because we've got a lot of numbers flowing around. We're doing products, we're doing addition, we're doing the addition of products. Take a minute and look at this to see if you can figure out the pattern here. Whatever our position is the row and the column. So here we have row 2, column 1. This is row 2, so we'd say row 2, column 1. Which means we took row 2 from A times column 1 to B. Here we have row 2, column 2, which means we took, again, row 2 from A times column 2 from B. So the first times the first plus the other product. Okay? So that is kind of complicated. If we look at an actual answer here, an actual problem, what I did is I color-coded some things so we could hopefully see them a little bit. So A elements are in purple, B elements are obviously in green. If I want to get this first position here, I'm going to take my row 1 times my column 1, because that is a position we call 1, 1, row 1, column 1. So I'm going to do 1 times 4 plus 4 times 9. And you see here they're so color-coded. I'm sorry, 1 times 5 plus 4 times 9. If I want to do still row 1, but now I'm in column 2, Well, that's going to change this. I'm still going to work with row 1 from A, but now I'm going to use column 2 from B. So 1 times negative 7 plus 4 times 6. And then if I'm going to do 2, 1. So now I'm going to move this to row 2, and I'm going to move this to column 1. So 3 times 5 plus a negative 2 times 9. And then if I want the last position here, I'm doing 2, 2. So row 2 times column 2. And that's going to give me 3 times negative 7 plus negative 2 times 6. And then we could just simplify those each. So 1 times 5 would be 5, plus 4 times 9 is 36, and that's going to give us 41. So that first element is 41. We could do the same idea for these other 3 elements, and when we do that, you get 41, 17, negative 3, and negative 33. So this looks like a big mess up here, but in the end, after we do that, we end up with just our 2 by 2 again. And this expands. You could extrapolate this whole process onto any size of a matrix. You could do a 3 by 3, you could do a 2 by 3 times a 3 by 3 and end up with a 2 by 3. And I know that's a lot of numbers. I'm throwing some things at you here. But really, as long as the rows of, or I'm sorry, the columns of the first matrix are equal to the rows of the second matrix, then we can do that product and we end up with a resulting matrix. It can get quite long and quite dirty, but it's always going to be doable. Like I said, I'm going to show you in Excel and on your TI-83s how to do it pretty quickly, where you just have to enter the matrices incorrectly and then tell them to multiply, and it'll work for you. Then it'll do a lot faster. So let's make sure we're bringing those calculators, and we'll see you next time.